Okay, so we are discussing about this principal component analysis, and I will start once again with the problem definition, as we considered that for dimensionality reduction, in this case, uh, you consider uh, your input space is a d-dimensional real space. So all your attributes, you consider them as a real variable. And in the principal component analysis, we would like to represent the input. We would like to project the input data points to a lower dimensional space, say dimension k, so that you have minimum loss of information. Now, this loss of information or amount of information is captured in terms of variances of individual components. So when you have a d-dimensional space, each dimension is giving you a component. And if you project a data point along any particular direction, for example, you have an input feature vector x, which is of dimension d, and consider a direction w, which is an unit vector. We should consider a unit vector in that direction in the same space, in the same dimension. Then you can project x on w, which means we discussed these things, that this projection operation is can be expressed in terms of matrix operation as w transpose x, and here I mentioned that x should be a column vector, so that this expression gives you a scalar value, because a projection will give you a scalar value, and the geometric interpretation of projection, as you all know, let me draw a diagram just to explain you. Suppose this is your origin, and say this is the data point x in a d-dimensional space, and you have a direction, any direction, and you consider that is passing through this origin. So along this direction, if you consider a unit vector along this direction, and if you project it, means you take the perpendicular drop on that axis, on that directional axis, then the intersecting point, you get the intersecting point, and you find the distance from the origin. So this is the value. So if this is the magnitude of the vector, as you know, the length of this vector, this is the magnitude, and after projection, you get the projected magnitude. Magnitude means, of course, with signed magnitude. Now, this gives you a projected value of x. So you consider for all the data points such a projection on a particular direction, and the purpose of principal component, finding out we define a principal component, is the component along that directions, components, or rather I should say the directions for principal component would be such that the variances of all these projected values, that should be maximized. That is the definition. And since as you are doing this kind of projections, as you know that variance, even if you translate the data point, translate the values, variance does not change, but it doesn't matter. But we can make a better interpretations if we move the, while doing this kind of transformation. So it's a transformation of a coordinate. As you can see that if I take d such orthogonal axis, and then we define a new coordinate space where along each axis, if you project them, so you get one coordinate transformation to another coordinate transformation. Those who are acquainted with geometric transformations, rigid body geometric transformations, you could easily find out that that is what we are doing here. We are doing for a single dimension, single direction, but you can take a set of d-orthogonal directions, and where you get all these components. So the idea is that one of these component should have the first thing, that direction should have the maximum variance. That is the first principal component. Now you go on, uh, you go on defining the next components as the direction which should be orthogonal to the direction of the first principal component. But once again, the variances along that direction should be maximum uh, uh, beside this first principal component's variance. So that it is along those directions. If you consider all possible orthogonal directions uh, of the direction of the first principal component, and the direction you should choose where the variance is maximum out of them. Once again, the same operation, same projection operations. So you perform the projections and you go on doing these things at each iterations. That means you find out the second component, as I was mentioning, then you from second component, then use the directions of first and second components, and then again you define a set of orthogonal directions. You can consider again another set of orthogonal directions which are orthogonal to both of these directions, and then you find the next highest variances, or the rather that directions where you are getting the maximum variance among those projections. So in this way, you can actually get a set of uh, orthogonal vectors, and along which you are projecting the data points, and each projection is giving you a component. So in the um, in the complete projection case of projections, that means from d-dimensional to d-dimensional, if you retain all the components, you are not losing any information. As you can see that if you have a coordinate space of a d-dimensional coordinate space, and you are simply considering a coordinate transformations from uh, one set of coordinate axis to another set of coordinate axis in the d-dimensional space. And as it's a kind of a rigid body transformation, you are not losing any informations. It's simply a coordinate transformation. So all the relative arrangements of the data points, they remain the same. But the interesting part is that now in this new transformation, you have certain directions where it is capturing the data spread better. So if I draw in the two-dimensional set of points, which I was trying to do in the last class, suppose we have this kind of, say, data points. Say this is a set of data points. And originally, your input space was defined with respect to this axis definition. So it's a two-dimensional space. Now, probably you might get something like this. Say this is one of the directions and this is another direction. These two orthogonal directions. You are translating your origin to the center of the data point. Now these two are the directions. And now if you project all those values, now if you express the coordinates with this new coordinate convention, so they are the new components. And if you can ensure that this proper maximum variances along each directions, starting from the first components, then actually they are all principal components. So this is the motivation. This is why the principal components are so useful, because you are trying to capture the distribution in this way. Let me give you another intuition. ij, then this sigma ij is the covariance of the attributes, say xi and xj. So x, I am assuming that x, the representation of x, let us consider it. This is a column vector, and there are d such attributes. Okay, there are d such attributes. This is a column vector, and x1, x2, x3, like this. There are d such attributes. So it is the covariance of, and each one is a random variable. Each one is a random variable because no, you have, suppose you have n data points. You have n data points. So you can represent your data set as the set of column vectors, right? You can represent your data set. I will come to all those representation later on also. So let us find here also. Say we can represent this data set as the set of column vectors. So I am using this bar to just to denote, because no, I cannot use this font, double font. I will be using bar to note. So this x1 and this x1 is different. This is simply the attribute, and this is the corresponding instances of this, or this is a data point. So you have, say, how many should be there entry, how many columns should be there for n data points. So there should be n columns. Okay, so this is my data matrix. Okay, so these are all column vectors. So now the question is that how do you express a express this sigma, this covariance matrix, using this this particular representation, using this particular representation. So what should be the dimension of sigma? What should be the dimension of sigma? That means the covariance matrix.
D cross D.
It should be D cross D, right? So the dimension of sigma should be D cross D. Okay, and if I consider the corresponding say the data point, say x1, this is x. So if I take for the covariance matrix, if I take x minus m, what is m? M is the if I consider, pardon, actually it should be x. This is I should also I should also subtract m later on. So this is not, this is, we should not consider this. For sigma ij, it is, as we have already discussed, it should be expectation of xi minus m minus, say, expectation of mu, right, into xj minus m. So that is the representation. I should say m1 and mi and xj minus mj. See, if m is the mean vector, if m is the mean vector, let me proceed with this mathematical treatise. So your objective function here, so that you can see that this is interesting, that your variance of z1 can be also expressed in terms of this covariance matrix. That means if you take the projection, of these data points, then if you compute the variance, which means this is the mean, so you can find out the corresponding expression of variance. Then you can show that this variance is nothing but this is equal to this one. So you can compute it. So that is why, to maximize the variance means, this is your objective function. Do you agree with this objective function? This is the constant optimization. So what is the constraint we have imposed, and what is this particular term, this coefficient, what is it called? This L, coefficient L, what is it called? Here in this case, this coefficient. And this is the constraint. Why this constraint is here? Anyone? So this is the constraint because we have considered that W1 should be, yeah, what should be W1? Magnitude of W1 should be
1.
1, right? Are you familiar with this particular notation? This is the norm notation. Okay, this is a L2 norm notation. Yeah.
Sir,
And
is that constant Lagrange's multiplier?
yeah, this is called Lagrange's multiplier. Right. It is a constant optimization. You are trying to maximize this by keeping this constraint, satisfying this constraint that your W, actually it is not W1, it is W because you are working on with the representation W. So the magnitude of your vector should be equal to 1. And in the scalar term, in the matrix multiplication term, this is equivalently expressed as W transpose W, right? So this is the objective function that you are going to optimize. Optimize means optimization, as you can see, we want to maximize this object function. And you know that what you should do is you should perform the partial derivatives with respect to W. And also partial derivative with respect to Lagrange multiplier will give you the same constraint. So we simply perform the partial derivative with respect to W and use that constraint in your equations. So what you get that if I perform the partial derivative, so with respect to W, you can, so this is the expression. This is again coming from linear algebra. You can see that if I perform this derivative with respect to W, so from here you get this particular expression. You can intuitively you can find out that no, there is some interesting analogy with respect to your derivatives with respect to your single dimensional variables, or I should say, yeah, single dimensional variables. Like this is a quadratic expression. As you can see, this is a quadratic expression, right? So when you perform the derivatives, so you know that if we have a variable, say x squared, derivative of x squared becomes 2x. In fact, that is what you are having here. You are getting here, say 2w, 2 sigma w. So, and you are getting here also, say 2w, right? So at w1, where actually you are trying to get a maximum, and there the derivative should be equated with 0. So you get this equation. That this is the equation, and finally, this is this is the form of your equation. Okay, is it clear? So this is a very no, familiar form in linear algebra. As you can see, that sigma is a matrix, right? Sigma is a matrix. In fact, it is in this case it is a square matrix. In this case, it is a square matrix, and also you can say it is a square symmetric matrix, because no, covariance is by the definition the elements are symmetric, and all the diagonal elements are also positive, as you can see. Now this sigma here, so this matrix, and this is the corresponding column vector. So you are getting the same column vector here. Okay, so this is actually that form of your the solution would be an eigenvector. And since you want to maximize it, so this value, this L should be for it is the maximum eigenvalue. Since you would like to vary, so what is the variance? You will find out the variance of this is given by this L, because if I put sigma W as say LW, then since W transpose W equal to 1, so finally variance is L itself. And since you want to maximize it, so this is what? This is the variance, W1 transpose sigma W1, that was the variance, and it is L, and since you want to maximize it, so in this equation, so there would be many eigenvectors and many eigenvalues, as you understand. But which eigenvalue you should take in this case, and which eigenvector with corresponding to that eigenvalue? it should be maximum, right? It is the maximum eigenvalue that you should consider, and that would give you the direction of the first principal component. So W1 is the eigenvector of sigma corresponding to the maximum eigenvalue. So that is the computation of the first component. Now, if I go for the computation of the second component, we will be imposing another additional constraint. Once again, as you see that we are trying to maximize variances, but now we have additional constraint that this W2 should be orthogonal to W1 also. One thing is that W2 should be a unit vector. That is the first constraint. Second is W2 should be orthogonal to W1, which is the first component, direction of the first component. So if I consider in terms of the if I use this Lagrangian multipliers, using Lagrangian multipliers, if I define this objective function for this optimization problem, you can see these are this is the form. So can you find out those constraints and the corresponding Lagrangian multiplier or coefficients? Okay. Say this constraint, it corresponds to that W2 should be a, what should be W2 with this constraint? What constraint it is specifying?
Unit vector.
W2 should be an unit vector. And what constraint it is specifying?
Null vector.
No.
Should be orthogonal to
W1
the
and
first
W2 are orthogonal.
component.
Very good. So this is because dot product of two vectors, that should be equal to 0. When they are orthogonal, the dot product of two vectors should be 0. So you get this W1 transpose W. That should be good because W you are going to maximize. And what is it expressing? What is it expressing? W transpose sigma W. Sigma is the covariance matrix of the data. Anyone? What we are trying to do with this optimization problem, what we are trying to maximize by satisfying the constraints?
Variance of the data.
Variance of the projected data. Okay. So this is what we are doing. So this is the variance of Z2, right? This expression gives you the variance of the random variable Z2 once you project on that. So you are satisfying all these things. So these constraints are important. Similarly, this is what we would like to do. Right? We'd like to get the direction of maximum variance by keeping W2 orthogonal to W1. By keeping the second direction of the second principal component orthogonal to the direction of the first principal component, and also the unit, it should be an unit vector. So by satisfying all these constraints, we can write this objective function in this form. And as we can see, L1, L2 are Lagrange coefficients, and this is just showing this. Now, if I take the derivative, this expression has been already shown here, that I am taking derivative with respect to W, because now if you take derivative with respect to L1 and with respect to L2, you get the same equation of the constant. So you can directly use those constant equation. Those properties you can use or equations you can use to derive, to reduce this equation further. So this is what we can, if once again you look at the particular format. This is 2L1 W2. I think here also it should be 2. No, this is okay. This is fine. Is it clear why it is L2 W1? Because this is just it is like a derivation of AX. A is a constant. You get A. So W1 is a constant here. So you get L2 W1. Right? But in this case, it is like a quadratic term, X square. So you get 2W2. I mean, to W, and then you are setting W at W2 for setting this equation. And then you get 2 sigma W, and then you put W equal to W2. Is this equation clear? Fine. So this is the equation, and let us see further reduction of this equation, that if I pre-multiply with W1, what do we get? We get this. W1 transpose sigma W2. So these are all scalar value, as you can see. And then we can find out that this is a term that 2 W1 transpose sigma W2 minus L2. Why? Because W1 transpose W2 equal to 0. Do you agree? So this term is equal to 0. So this reduces to this equation. Okay, and this term is equal to 1. This is equal to 0. And this is equal to 1. Is there any doubt? So this is what? So now, since W1 transpose sigma W2 is scalar, so in fact W2 transpose sigma W1 is also scalar. So we can write in this form and replace sigma W1 by LW1. So we can write it in this form, right? So W2 transpose sigma W1 is 0. So hence L2 equal to 0, right? So now this equation can be written in this form, that once again you see it is again in the form of your eigen vector equation. That means it is an eigen, W2 should be also an eigenvector of sigma, that the same covariance matrix. So W1 was an eigenvector that was corresponding to maximum eigenvalue. Now W2 will be also eigenvector, and that will correspond to the next maximum eigenvalue. So that is what we'll see, that W2 is an eigenvector and L1 is the variance, naturally, using that expression. So the solution for W2 is that it is the second maximum eigenvalue, eigenvector corresponding to the second maximum eigenvalue. So you can extend it. So what is this? What are the principal components in that case? Can you give me in the form of a theorem, if I say that if I have the covariance of the data point, how do you get all the principal components?
By finding the eigenvectors of the corresponding eigenvalues, if I go from higher to lower order.
That's right. Very good. Right. So you get, in fact, you will find them, all of them, as positive, and it could be minimum, it could be 0. Right. So this is the algorithm, right? Yeah.
Sir, so when we were trying to compute the second direction segment of finding the projection, instead of doing this Lagrange multiplier operation, can we make this kind of an comment that since the covariance matrix is symmetric, so for symmetric matrices the eigenvectors are orthogonal to each other. So
right.
Since I have got the first one along the first eigenvector of the highest eigen value, then and I am looking for an orthogonal direction, so automatically won't that direction be corresponding to the another eigenvector of the second highest value?
No, that is the variance of the data, and that you are proving here. So that is related general result from linear algebra, that you get those eigenvectors and their corresponding variances. But it means that your projected variance would be the second eigenvector. It just shows it. It is not really directly deducible in that form. So these properties are related. I should say, they are corroborating. The facts are corroborating. But if you consider your problem, objective is that you are trying to maximize variances along a direction which is orthogonal to the direction of the first principal component. Now that needs to be proved in this manner.
Okay.
Okay. So in fact, now you can show it for, and this result is consistent with respect to what you are saying, that with respect to this kind of transformation, orthogonal transformation, and other things. You can interpret in various ways. So what is the algorithm for principal component analysis? If I just look at from the algorithmic point of view, as you can see that in our case, we are also centering the data. To the data center. We are bringing the origin of the space to the data center. So that's why this translation of the corresponding data point is there by the mean of the data point, x minus m, where m is the mean of the data point. And what is W here, capital W here? Can you tell me? Can you guess what is capital W here? Actually, I have defined it here also. Right? Each column vector is a d-dimensional column vector. W1, W2, they are all d-dimensional column vector, and each one corresponding to the eigenvectors. And starting from first to, say, in this case, since I am discussing with respect to the dimensionality reduction, so I will say that this transformation, I will take, say, k eigenvectors, and starting from the first maximum eigenvalue, and in that order, I will consider, say, k directions, and each one of unit vector and each are eigenvectors of the covariance matrix, and then I perform this transformation. So this is the dimensionality reduction. Do you agree that there is a dimensionality reduction? What should be the dimension of W transpose? What should be the dimension of W here? What is the dimension of W?
K cross K.
See, this is a column vector. How many rows? D rows. And how many columns? K columns, right? So it is D cross K.
After transpose, it becomes.
So yeah, transpose is, if you have answered for transpose, then it is correct, right? It is K cross D. So this is K cross D, and what is the dimension of x minus m? I hope you have understood. What is x?
D cross K.
D cross. See, what is the dimension of x? X is a column vector, no? It is D cross 1. What is the dimension of m? M is a mean vector. It is D cross 1.
So D cross.
Right? It should be D cross 1.
Yes,
Any confusion? Then what should be the dimension of Z?
K cross 1. K cross 1.
K cross 1. This is the dimension reduction. You have a D cross 1 data point. That means D-dimensional data point. Now you have a K-dimensional data point. What are the properties will come later on, but you should understand that actually by ignoring some of the components, you are reducing dimensions. So you are finding out you can compute all components, all principal components starting from first to dth, but no, you are considering only, say, first K components. There are certain criteria by which you can decide how to ignore. In fact, in your assignment, I think this is also given. So you have to apply this particular theory. So if I just simply describe this algorithm, as you can see, you have to compute mean of data points, then translate all data points to their mean. This is the performance of this x minus m. Then compute covariance matrix of the set. So that's why I was telling you that actually after translation of each individual points, then you are computing covariances. So how do you express this covariance matrix in terms of matrix multiplication? Can you tell me? How do you express this covariance matrix? Say, let me express x equal to, let me express it as I was mentioning, these are all column vectors. x1, x2 to how many data points? How many data points we should take? We have described what should be this. I'm using the bar to show that they are vectors. Now, don't confuse them with attributes, single dimensional attributes. So, how many data points? Let us take n. This is your data matrix, representation of your data matrix. Is it clear? In the matrix form, you represent. So, each element, each column is representing a data point. Each one is a column vector. So, what should be the dimension? Dimension of this x?
K cross 1.
D cross n.
Very good. D cross n. Right?
X1 or X, sir?
Pardon?
Sir, you are talking about X1 or X?
X was a random x was a random variable of a data point. So if I consider any random variable data point, I will represent it like that. This is instance. This is the first instance, second instance, like this. That was the kind of representation we have used, like variable x, and then you use x1, x2 to instantiate them. But this is a data matrix. I'm using this capital X just to show this is the data matrix. So this is the data. This is the random variable in abstract sense. This is a random variable. So now you translate with the mean of the data point. So let me use another symbol x tilde, which is the translated one. How I should represent it? Translated one. How this matrix should be represented?
X1 minus M1, X2 minus M.
That's right. X1 minus M, not M1. So mean is same. There is a specific mean vector. There is a specific mean vector of this random variable. It is associated with random variable of the distribution. It is not M1. It is not associated with attribute. Sorry. So this vector will have again mean of different attributes. This is a vector. Mean is a vector. So it will have attributes, say M1, mean of attributes x1, x2. So please forgive me that I am using similar pronunciations of attribute variables, and so you should. That's why bar sign is there to show that they are actually column vectors. And when I am saying attributes, it's a single dimension.
Sir, hello.
Yes, please.
Sir, can you repeat once about that M?
Yeah, that's what I'm saying. M is a mean vector, mean data point. So you concentrate on this representation. What is meant by mean? Mean of this data point. What is meant by mean of this data point? How do you compute mean? M equal to, you tell me. This matrices needed, so you just add them. No? You add all these matrices. You add all these matrices and then you divide it by n. Did you get my point? Divide it by n.
Sir, adding all the vectors, column vectors, right?
Adding all the column vectors. You are right. Adding all the column vectors and you divide by n. That is mean. So that's why m is also a column vector.
Yeah, M is the mean column vector.
Mean column vector. So that's why individually I am subtracting each column vector, subtracting mean vector from each column vector. That is what means by this translation. Is it clear?
Yes, sir.
It is clear, no? So this is I am calling x tilde. So this is a transformation from x to x tilde. And what is the dimension here? Dimension of this data?
Same. That will be the same.
Same. Dimension should be same. So now the question is that what is the covariance matrix? So now you see I have already taken care of mean. So the mean of individual variable, individual random, if I consider mean of these data points, mean is always 0. Okay. So what is the covariance matrix expressed for x tilde? how do you express the covariance matrix? So what is covariance? Covariance of these data points, x tilde. How do you express them?
X tilde into X tilde transpose by n.
Yeah, by n, right? It is basically x tilde into x tilde transpose by n, right? That is the covariance matrix. Is it understood? If I consider a particular column vector x1, so if I consider a particular column vector x1, let me go back and then rub these things. Okay. So if I consider a particular column vector, say x1, so which means I'll be writing, say, for example, x11, x12, I'll be using that second index to denote the corresponding attributes, dimensions. Say, I'm using the other way. I should have used, anyway, let us use this, x1d. And consider the another column vector, say x21, I will be taking its transpose x22 to x2d. So if I perform this is called actually outer join, right? Outer join of a vectors, right? So if I perform the matrix multiplication, I will say actually we are getting all possible pair of products, right? All possible pair of products in a particular matrix. It will give you, what is the dimension of this matrix? It should be
one cross one cross.
No, it is d cross 1 into 1 cross d. It should be d cross d. That is the difference. No, that is why I say that column vector representation is important when you are. If I use a row vector, for example, if I pre-multiply it, then dimension would be just 1. That is a scalar. That is the dot product of two vectors. But when I take the outer product, it is simply product of all possible pairing combinations, and there is a order. So if from the random variables point of view, as you can see, this outer product is giving me the observations of products of all possible combinations at individual fields of the matrix, elements of the matrix. And that is what you are trying to compute in the covariances. Huh? Basically, you are computing the product of, the data points, product of the corresponding data points, and then the instances, and then you are subtracting mean from it, the average of that, and then subtracting the product of mean 1 by n into, as you can see, I mean, in the covariance expression, it is the average of your product of two random variables, say x, y, and minus the product of average of two random variables. That is what is the expression of covariance. If I consider, of course, this is a reduced expression, it is actually the product of the deviations from the mean of individual random variables. In what way you describe in the textual form. So finally, this is what we are computing when you say that no, x tilde x transpose. That is what we are doing it. So let me rub once again too. So let us proceed. That anyway, that covariance matrix computation I will come. So after computing covariance matrix, simply then you have to find out this eigenvector. So there is a standard method of computing eigenvectors, and from there, uh, if you order them, you choose k eigenvalue, k eigenvectors, ordering them from their increasing order. Sorry, it should be in decreasing order. Decreasing order, starting from the first component is the highest eigenvalue, so it should be in decreasing order. I have to you should correct this part later on, and choose k such that the fraction of variance accounted for is more than a threshold, which means as it is always no, ordered in terms of reducing variances. So you see that what is the total variance? The total variance is sum of all these variances. So what is the fraction of variance that you find that no, if I don't use the rest of the components, that means d minus k components. So what is the variance you are losing? If this loss of variance is insignificant, for example, I have given you that example of planar arrangement. The third orthogonal axis with the third eigenvalue, it should be 0, which means there is no variance at all. So you can simply remove it. So it could be also a very small amount of variance due to noise. So you may remove it, and you consider that your data is sufficiently represented by only these k dimensions. So this is what is your dimensionality of data is there. And there is some examples. Maybe I would discuss this example in the next class. And as I told you that I will take an additional class on Tuesday, that is at 8 p.m., where I would further discuss about this technique.